way to choose L vertices on a graph so that if you initiate your random walk there, then the convergence rate is controlled by lambda L plus 1, right? So it's just there exists. And we've actually constructed it. We constructed the measure. So the properties that the measure had was that it was some W non-negative. It's a measure, so let's assume that its one norm is 1. And then it had the property that it made 0 inner product with the first L eigenvectors, right? This is how the measure was constructed. It had this property, right? Okay. And then it also had, it averaged the, okay, it did something more, right? It also had phi1 transpose W was 1. So we normalized it so that it's like that, okay? So we found that. Okay, so let's think about what this actually means, okay? So this has more meaning than we realize, these equations, okay? All right, so, and the key thing was that the support of this W was small, right? So support of W was less or equal to L, okay? So it didn't need all n coordinates to do this, just needed a few coordinates. Okay, so let's think about what this is saying. So I want to take, can you see everybody over here? Okay. So I want to take, so there are two separate things going on. There is this going on, and then there is this going on, right? So let me write this generally. So if I write this generally, this is phi jw is equal to 0, where j went from 2 to L, okay? So there's that going on and this going on. And W had these other properties, which I'm not putting in a box. Good? Okay, so let's think about what this means, right? So remember, we're thinking of eigenvectors as functions on the graph, right? Phi of, if I take eigenvector phi, its first coordinate is a number sitting on vertex 1, second coordinate is a number sitting on vertex 2. That's how we saw all those pictures, right? You saw the eigenvector going smoothly and all that. So think of these as functions on the graph. So each phi is a function on the vertex set of the graph. So that means it's a function from n to r, and vertex I is getting sent to phi I, the ith coordinate of phi, okay? So every eigenvector you should think of as a function on our graph, okay? So now let's think what this is actually doing, right? Let's look at this box. So if I look, so phi1 transpose W is equal to 1, If I rewrite it, this is saying that sum of phi1i, wi is 1, okay? I'm just doing this very slowly. So I have a weighted combination of the function values that's giving me 1, okay? And that's true on the one side. But on the other side, if I think of, so how do I want to think of this? Yeah, so let's assume also phi1 is just the all ones vector. Okay, I haven't normalized it, so it's just the all ones vector. So what happens if you take the global average of phi1? So if I just sum phi I over all I in n, and so this is the global average of phi1 over the whole graph. Do you agree? Okay, so I'm going to do some things in a minute. So I'm writing two separate things, okay? So phi1 is 1, is the all ones vector. So if I take the global average of the function value of phi1 on the whole graph, I'm taking phi11 plus phi12 plus phi13 plus up to phi1n, and dividing by the number of vertices. That's the average, right? So the global average of the phi1 function on the whole graph is this. Do you agree? But if phi1 is 1, what is this? Also 1, okay? So what we just did with the W is that we found, this is the global average of phi1 on G, on the graph, okay? And what the W is achieving for us is a weighted average of just some of the indices. So I lies in the support of W, right? I don't need all the I's from 1 through N. I just need the W, the places of W that are positive. So if I vary the I over the support of W, which might be very small, because I may have a W that's supported on 5 vertices and there are 1,000 vertices in the graph. So what the W is achieving for us is that the weighted average of phi1 over this very small set is also 1, okay? Is the same as the global average. That's what this W is actually doing for us, okay? So it's finding you a weighted average where you only have to pick a few vertices, weight the value of phi1 on those vertices, take the sum, and that's giving us the same thing as the global average, okay? So that's happening with phi1. Let's think about the other guys, these guys, okay? So what's the global average of one of these eigenvectors, the ones that are past 1, like say phi2, okay? So global average means what? I take let's take phi2 of I, sum over all I, and then divide by 1 over n. This is the global average, right? Do you see what this has to be? It has to be 0, right? Because this expression is the same thing as phi2 transpose 1, okay? And then there is a 1 over n, which doesn't matter. But phi2 is orthogonal to 1, so this is 0, okay? So the global average of every other eigenvector is 0 on the whole graph, okay? The global average of the first eigenvector depends on how you normalized it. If I set it to like this, it's 1, good? But otherwise, all the other guys have global average 0, right? But what is this achieving for us? This is achieving, let's write that part, this part, okay? This is saying that if you take the sum of phi j I, wi, over all I in the support of W, because that's the only places where W is not 0, if I take this weighted average, I also get 0, okay? So weighted average is the same as global average. That's what this W is actually achieving, okay? You've seen this before, right? Do you remember Simpson's rule from calculus? It allows you to integrate a function on an interval by just calculating the value at 3 points. Remember Simpson's rule? Yeah? So I'll write Simpson's rule here because I think I don't remember it offhand myself. So Simpson's rule says, so this is first year undergrad. So this says that if you want to integrate a function over the interval from a to b, so this is a, this is b, then, so I want to, this is my function, I really want to integrate, so I want to calculate the area under this function, that's the integral. I only need to calculate this, so this is roughly the same thing as doing b minus a divided by 6 times f of a plus 4 times f of a plus b divided by 2 plus f of b. This is Simpson's rule, okay? So what is this actually saying, right? It's saying that I need the function value that sits on top of a, I need the function value that sits on top of b, and I need the function value that sits at the midpoint. This is a plus b divided by 2. Okay? So I only need 3 function values, but I have to put weights in front of them to get the full integral. Okay? So what are the weights? So fa I have to weight with b minus a over 6. This is the weight I have to put on top of this value. That one is 2/3 b minus a, and then the last one is b minus a over 6. So these are like our w's. These are the weights, okay? So you can pick 3 points and get roughly the same integral, which is the global average, by weighting the special points, okay? So there's a special way to pick these points. Okay, Simpson's rule, not so special, but there are other rules like this.
So what is the assumption on F?
Maybe some continuous function. I think there's no assumption even. Maybe let's assume continuous function.
Not polynomials.
No, I don't think you need anything like that. It's only roughly.
Interval can be any arbitrary interval.
Yeah, but finite. A to B.
But nothing on the size of the low.
No.
Actually, if you put the B minus A on the other side, the weights are just 1 by 6, 2 by 3.
Yeah, that's right.
Because that's the average will be a 1 by 3.
Oh, yeah, that's right. So if you do 1 over B minus A here, then you don't need this B minus A, you're saying?
And the weights there.
Yeah, okay. Yeah. So let me just leave it the way it was for a moment. But you get the idea, right? So this is how the computer does integration. It doesn't actually integrate on a continuous domain, right? It actually picks points cleverly. It finds function values at those points. It weights it cleverly. It gives you the integral. It discretizes the interval, right? That's kind of calculus, right? You put these little bars, you sum up the areas of the bars, and you let the bars go to infinity. That's kind of the width go to 0. Yeah. This Riemann sum or whatever, like the sum that we do. Okay, so this is saying that the global average can be gotten by just picking points in the domain cleverly, but attaching weights to those function values and then adding, and you get the same thing. Okay, you get the global average. So that's exactly what we just did, if you think about it. Right? So what we did, this W, what it achieved for us, is that it could average all the eigenvectors from phi1 to phi L by attaching weights to certain coordinates. Okay, so I'm going to go to the slides now. So, for example, if I have a graph, some complicated graph, it's not going to be complicated enough because I think humans can't do random things. Okay, so if I want to find the average of a function, one of the eigenvectors on the whole thing, I don't need to look at all the 1, 2, 3, 4, 5, 6 points, but I may just take the value here, and I may take the value here, I might put a weight here, and I might put a weight here, W2, and that's all I need. Those two are going to already give me the global average. Okay? So this is like the cholesterol function example from yesterday, right? If I want to calculate the cholesterol, so I have a cholesterol function of everybody who is between age 20 and 25 at IISc, let's say, and they're connected by something, maybe people who have the same sort of genetic pool, we connect them together, or something, some medical way we connect them. And we'd like to know what's the global average, what's the average cholesterol of 5,000 students or whoever. I don't know how many go here, but some large number of students. Let's say we want to know, let's make it bigger, like 100,000 students. I want to know the cholesterol of 100,000 students who go to certain types of institutions, because all those pegs many other things. How do I do it, right? So I have this huge graph. So what I would like instead to do is to just cleverly find a few students and average their cholesterol, but weight them in some clever way so that I can actually achieve I can see the global cholesterol figure by just looking at the small sample. Okay? That's what this W is allowing us to do. So I'm going to define these things. These are called graphical designs. So the support of W is mostly what we're going to care about. That's where should I put the weights, which vertices should I pick, okay? And then you can also work out the weights, but let's not worry about the weights for a moment. Let's just pick at least the support of the weights, okay? And this thing is telling you that you can average a whole bunch of eigenvectors with weights have support at most L, okay? So okay, I didn't fully connect all the dots. Cholesterol function, okay? It's fairly smooth. If I take a population like 20 to 25, connected by some edges, right? You guys are all roughly the same age. You're all from the same, nation. So all these things control cholesterol, right? So if you're like from a completely different ethnicity, like if you're African versus Caucasian, your cholesterol works differently, okay? So you guys are all roughly the same. And so if I have a cholesterol function, then it is in the span of the first few eigenvectors of the graph. That's what I showed you yesterday, right? When the eigenvalues are low for the Laplacian, the eigenfunctions are fairly smooth. So if I have a smooth function, it's in the span of the first few eigenvectors. You don't need the high eigenvectors to write the cholesterol function, okay? So example, it could be in the span of phi1, phi2 up to phi L, okay? If that is, and I want to average that function, it's enough to average the things, the phi1 through phi L. Do you agree with that? So if I have a function that is, what I'm trying to say is, if I have a function that is the span of, so if this function is some combination alpha I phi I, where I goes from 1 to L, okay? I only took a few, and I want to find the global average of this. It's enough to find the global average of these phi I's, right? Because what's the global average? It's the sum of phi V over all V in the vertex set. This is the global average, okay? That's the same thing as sum of alpha I, sum of phi IV over all V, like that. So if I know how to average these things that expresses F as a combination, then I can also know how to average F, okay? So that's why we're going to try to average eigenvectors, because we're interested in averaging functions. If they're sufficiently smooth, they're going to be in the span of low eigenvectors. So I'm just going to average those eigenvectors. That gets me everything. Okay, now I've connected all the dots.
No, but there's a slight caveat here.
What's that?
Because you have changed the order. So your phi i's here corresponded to eigenvalues ordered with respect to absolute value. Earlier,
Yeah. So that's true. But sort of in principle, okay? So in principle, what we want to do is we have some function that's in the span of some eigenvectors. I'm claiming it's enough to average the eigenvectors. If you can do them, you can also do the function, okay? Yeah, you're right. So we flipped matrices a lot, but in the end of the day, it's not going to matter which one we use. But this is just my intuition. Okay, now how do I make this go up here?
it's already on.
Yes.
Just
Escape, maybe?
No, it's coming.
It's coming? Okay, we switch off some lights. 4. Okay, I think we'll get through this. Okay, so this is going to be like hopefully relaxed talk, movie time. So you can like look at some pictures and tell me what's happening, okay? So this is just a picture of a graphical design. So this is some particular graph, and this is a collection of vertices that can average a certain number of eigenvectors, okay? So I haven't given you any details, it's just a picture. Okay, so where does this intuition come from, right? So the intuition or the motivation came from the notion of spherical designs, or Simpson's rule, if you like. Okay, that's another type of example. But what's a spherical design? A lot of people work on this. The Fields Medal to Marina Vyazovska came from work related to things like spherical designs. Okay, it's a very hot topic. So what people are trying to do there is that you want to average functions on a sphere. Okay, this is continuous math, like this is analysis. So you want to average functions on a sphere, and you can ask, okay, which functions should you average? And it turns out the right functions to average are what are called harmonic polynomials. Okay, it doesn't really matter what they are. Okay, you can think of them as polynomials in x1 through xn, if the sphere is living in Rn. They're polynomials in x1 through xn that are, that's right. So they are polynomials of degree up to, they increase in degree. So there are degree 1 harmonics, there are degree 2 harmonics, degree 3 harmonics, and so on, forever, okay? So there are these things called spherical harmonics. And what you want to do there is the same thing. I want to look for a set of points on the sphere, x1 through xn, and weights, ai, such that for sufficiently smooth functions f, the global average of the function on the sphere, so this is the integral of the function divided by the volume of the sphere, should be roughly the same as the weighted average of the function values at these special points. Good? Same idea. So it's like numerical integration. These are also called quadrature rules. Maybe you've heard of Gauss quadrature, which is like a very special way to do integration. Okay? So these are spherical designs. So how do we find, so if I want to integrate all functions of degree up to 5, which point should I use? If I want to do all the way up to degree 10, which point should I use? Okay, so depending on the degree of your function, you need different points. So here, for example, is a spherical design that integrates all in general, a spherical T design is a collection of points that integrates polynomials of degree up to T. Okay? And the picture is a picture of a 5 design. So those are the vertices of an icosahedron that is inscribed inside the sphere. Okay? Because it's a sphere, you expect these points to be very symmetric, right? You don't expect some badly placed points with some crazy weights. What you expect is like some nice configuration of points with uniform weights, just the same weights, okay? So most of the time we can get away with uniform weights if your space is very symmetric, like in this case. Okay, so these are spherical designs. People work on this, right? Like what's the size of, is there always a design of size at most such and such? Those are the kinds of questions they want to ask, okay?
As n increases, it will give better results, right?
That's right, yeah. If you have more points, you will get better results. That's for...
vertices have nothing to do with that number 5, right? It's just that on those vertices, there is a function which is a polynomial of degree at most.
No, it's saying that if you pick these corners, so you inscribe this icosahedron inside the sphere, and you pick these corners which are on the sphere, okay, then the function value there with uniform weight will average the function on the whole sphere as long as your function is a polynomial of degree up to 5. That's what it's saying, okay? So up to that degree, those points will do the job, but there are many, many other choices of points. This is one collection of points that will do the job, okay? So think of those points as the support of W, right? The weights are just uniform in that case. So this was the motivation for defining these graphical designs by my colleague, Stefan. So let's now pass to graphs, okay? So how do we do this on graphs? So we've already seen this in this course, but I'll do it again. So I have a graph, finite, simple, connected. I want to pick a collection W inside the vertex set with some weights, AW. And we say that that collection with the weights averages the function f if the weighted average of the function with these weights on the vertices in W is the same as the global average. Okay? So this is the definition of averaging. All right, so W is the collection of vertices that is small with weights such that the weighted average of the function on W is the same as the global average. Okay, so let's do an example. Peterson graph. This is the Peterson graph. Let's take this function over here. This is a function on the Peterson graph, right? I'm putting weight 1 on vertex 1, 0 on vertex 2, minus 1 on vertex 3. So you see here 1, 0, minus 1, minus 1, and so on, right? 1, minus 1. So I put some numbers on the vertices. That's the function, right? Now, it turns out that I can just pick the red vertices with uniform weight, and if I just average those values that sit on the red, I will get the same as the global average. Let's calculate the global average real fast. Do you see what the global average is? Sum up all these numbers. It's 0, right? 1 minus 1, 1 minus 1, 2 minus 2, minus 1, 1. Okay, this is average 0. So now look at the red vertices with the weights, with uniform weight. Okay, I'm just using uniform weight. And just...
So uniform means 1/5 or 1?
It doesn't matter, it's going to be 0 at the end.
Yeah.
But let's make it 1/5. Okay, you can make it 1/5. So whatever it is, you have 1/5. So let's say it's 1/5 is the weight, but 1 minus 1, minus 2, 2, and 0 will also give me 0 times 1/5, doesn't matter, I'm still 0. Okay, so the red vertices will average this function with uniform weights on the red vertices. Got it? So this is an example of a W. W is now 5 vertices out of the 10 vertices of the Peterson graph, right? The weights are uniform, that's why the color is just all red, okay? Now let's go to this function. It's the same function, I think. Yes. Okay, so here is a different collection of vertices that will also average that function, okay? But now the weights are a little bit different. So pink means that it's a different number from red, okay? So different shades of red are going to be different numbers. So now the weights are put weight 1/3 on this vertex. So I get 1/3 times 1. Then you put 1/3 on vertex 4, which is it's one of the pinks.
The rightmost.
Yeah, it's this one. Yeah, so that's 1/3 minus 1/3. No, sorry, 1/3 plus 1/3, 2/3. And then another 1/3 over here. Okay, so that's 1. And then you put weight 1 on this vertex. So that's a minus 1. And that comes back to 0. Okay? So this is a properly weighted, this is like a more interestingly weighted subset of vertices that will also average this function. Okay, so there are many choices. There's the uniform one we saw first. Now there is another one. But you see, when you allow weights, you can get away with 4 vertices. Before I needed 5 vertices, right? Now I can do 4 vertices. So you can ask, how small can you do if you allow weights? Okay, you want the weights to be non-negative, because quadrature usually works like that. You could, in principle, make them whatever, but non-negative is the nicest. Okay, integer is even nicer. Uniform is the best. Okay, but uniform, we'll see, doesn't always work. So there may be no collection of vertices that are uniformly weighted that can average your function. But if you allow weights, you have more flexibility, you can do this. Got it? This is what it means to average. So instead of integrating, we're averaging. That's the difference. Okay, so this picture is the same picture as last time. I'm going to work with the AD inverse matrix, so walk matrix. This is just to show you like how the eigenvectors change, right? So when I look at the first eigenvector by frequency, then it's going to go smoothly. And then when you go to the second eigenvector, it's also fairly smooth. And then when you go to the next one, like the 11th one, it jumps all over the place, okay? So across an edge, the variation is large as the eigenvalue increases, okay? Anyway, this we saw yesterday, so let me just skip this. Yeah, so this was just some motivation, right? If you have a smooth function like rainfall over the United States, you make a graph, that's the graph, the US graph with a node for every state connected by an edge if the state shares a boundary. Then if you want to express this rainfall function, you just need the first few eigenvectors. That's the idea, okay? So that's why we can do this. Okay, so now here's the definition. This definition is it's sort of due to Stefan. It's a slight modification, but let's stick with that. So graphical design definition is you start with a graph, okay? And we order the eigenspaces in some way, okay? Any way you want technically, but let's assume we order them by eigenvalue, okay? So
of the adjacency matrix?
it doesn't matter which one actually, but in this slide we're doing AD inverse. The walk matrix, 1 over dA, okay? In these slides, everything is set up for 1 over dA. But you can do it for Laplacian, or you can do it for adjacency, whatever you want. But it has to be symmetric. That's important.
These are like subspace inclusions.
These are subspace. No, they're not subspace inclusions or anything. These are different eigenspaces. They're not included in each other. But I'm ordering them. I'm saying according to eigenvalue, let's say. Okay? But in general, later, when you think about it, you'll see it doesn't matter which way you order it. You can do whatever you want. But let's order them by eigenvalue, okay? Except that the first one is always the trivial one, the span of the all ones, okay? So lambda 1 is always the span of the all ones. Okay, so let's assume we have ordered them by eigenvalue, okay? Eigenvalue increases, it's going up. Okay, so then a K graphical design is a subset of vertices W with real weights that averages the first K eigenspaces, not eigenvectors, eigenspaces. That means I want to average every single eigenvector, a basis of eigenvectors from those eigenspaces, okay? So you can average eigenvectors if you want, but I'm just going to average entire eigenspaces at one shot, Okay? There are some complications if you start cutting eigenspaces in the middle. That's why the definition is like that. So if there are no multiplicity, somebody asked about multiplicity yesterday, then we are really averaging the first k eigenvectors. But oftentimes in structured graphs, there are fat eigenspaces. So I don't want to cut them because I don't know which part of the eigenspace to take. So I'm just going to average the whole thing, okay? So we're going to average the first k eigenspaces. And so if W can do this with some weights, we call that a K graphical design. Is the definition okay? We'll see lots of examples in a minute. Okay? So this is the idea. Lambda 1 is always the span of all ones. Then lambda 2 comes with the next eigenvalue. Then lambda 3 with the next eigenvalue. We're using the walk matrix, so it's ordered by absolute value, right? So we're marching up, marching sort of down, I guess, in absolute value. And we're looking for a subset of the vertices with weights that can average the first k eigenspaces, right? That means if you have a function that lies in the direct sum of those eigenspaces, I can also average that, right? Because I'm averaging a basis for those eigenspaces, so I can also average any function in the span of those in the direct sum of those eigenspaces. This is okay? Question? Okay. So now these weights, what about these weights, right? So the weights are always real numbers, and if I don't impose anything on the weights, we'll just call this a weighted design, okay? So design is the collection of vertices plus the weights. So we'll call this a weighted design. If it's non-negative, then we call it a positively weighted design. This is the type we really like, this middle one. And if it is really like 0 or 1, meaning that all the AWs are just 1, or 1 over whatever, uniform, then we call it a combinatorial design. Good? So do you see that this W we produced is a design, right? Because what is this W doing? It's averaging the first so many eigenvectors, right? That's what we just calculated here. This W is a weighted average of the first so many eigenvectors. You can assume that we've taken all the eigenvectors from the eigenspaces we care about.
So can weight be 0? Like if it is 0, we can ignore it.
Yeah, you can. So yeah, so you really want W to exist with a positive weight or a non-zero weight on every W, right? If it's a 0 somewhere, then drop that from the W, correct. Okay, so this is the definition. This is good? Okay, so let's do examples. All right. So this is the graph of the icosahedron. Okay, so I take the graph of the icosahedron. That means just the edges of the icosahedron. Okay, so that graph, it looks like it is a graph of the icosahedron. And I look at the walk matrix, this AD inverse. This is a regular graph. Yeah. So AD inverse is just 1/5 of A. Okay. And then its eigenvectors are organized in the rows of this matrix, okay? So the phi, or the phi and the psi in these slides are the golden ratio and the other thing, okay? It's 1 plus root 5 over 2, 1 minus root 5 over 2. So sorry about the notation confusion. It's not the same phi. This is just a number, okay? So this is the first eigenvector. It goes with lambda 1 equal to 1, okay? That's the eigenvalue. This is the next eigenspace. The next eigenspace is 3-dimensional, and these 3 rows are the eigenvectors of that spanning that eigenspace. And then there's one more eigenspace for lambda 3, and then there's one big eigenspace for minus 0.2. Got it? So this graph has fat eigenspaces. There are 4 of them. The first one is trivial, and then there are 4 of them. Okay, so homework for you guys in the sheet is to show 1, every subset of vertices will average the all ones. The all ones is kind of useless or trivial. Any subset of vertices you pick, you can put uniform weights on it, it'll average the all ones. Okay, so we usually don't worry about the all ones because whatever works for anything else is going to work for all ones too. Okay, so every subset will average the all ones with uniform weights. And no proper subset can average everything. These are 2 homework problems. Okay, so you can't hope to average all the eigenvectors with a proper subset of the vertices. If you try, you'll end up taking all the vertices. Okay, so what we're interested in is averaging lots of eigenvectors, but not everything. And we don't care about the first one, because the first one will work no matter what set you pick. Got it?
No proper subspace.
No proper subset of vertices can average all the eigenvectors. Every single one of them. Okay? If you try, you can write the proof, you'll see a contradiction. And so those are 2 exercises, you can think about it at home. Okay? All right, so that's written in the exercises. Okay, so these are the eigenvectors. Everybody okay with this? Yeah? Question? Oh. So now what we want to do is I want to average, say, the first one is for free, but let's say I want to average this eigenspace and that eigenspace, or just this eigenspace, or this one only, or whatever. You can order things whichever way you want, okay? Doesn't matter. So in this example, I have ordered the eigenspaces in this funny way, okay? I put lambda 1 first, always has to be first, but then lambda 4 comes next, then lambda 3, then lambda 2.
Lambda 4 is the 5 dimension.
Exactly. So I've just picked some random ordering. Lambda 4 is this 5-dimensional subspace. That's the one I want to average. So I want to average the first one, which is for free, and this one. And I don't care about the others. Good? That's what this next slide is saying. So in blue, I'm telling you I want to average lambda 4, which is the last 5-dimensional eigenspace. And I don't care about lambda 3 and lambda 2. Okay? So I've ordered in such a way that I want to average the first 2. So you have a choice of ordering. You have a choice of how many eigenspaces to order, to average. And yeah, that's all. Okay? So you can choose all that. Okay? So I'm choosing to average lambda 1 and lambda 4. I don't care about the rest. So for example, here are the 3 types of designs here are examples of 3 types of designs. If you allow any weights, okay, positive or negative, this colored vertices will average that 5-dimensional eigenspace, okay? And the blue is a negative number, the pinks and reds are positive numbers, but they're all slightly different numbers, okay? If you only allowed non-negative weights, then these colored vertices can average the 5-dimensional eigenspace. But now you see you need more points because you're restricting the weight, right? You're not allowing any weight, you're restricting the weight. And now if you ask for a uniformly weighted collection, there is none.
What do you redesign?
Yeah, so I'm just
It's
thinking of,
redesigned, right?
yeah, so, yeah. So this should be 2, yeah, so there's some problem with that. So ignore the 3 and the 2, please. I think there is some error with that. But the statement is correct, okay? So I'm just saying that 1 and 4 can be averaged by these guys if you allow any weights, by these guys if you allow non-negative weights, and you cannot average with uniform weights, okay? With uniform weights, you can average only something smaller, I think. Okay, so I'm also confused by the error in the notation. But that's roughly the idea that we're doing here. Okay, we'll move on to other examples. Hopefully there's no error there. Okay, so then, okay, so that was one thing. And then we also have another notion of something called an extremal design. So extremal design is when you can average all the eigenspaces except the last one. It's called an M-1 design. So you can average everything except the last one, okay? So this is very closely related to something called the Erosh-Corrado theorem that you may have heard of in combinatorics, okay? So these extremal designs have some nice connections to like combinatorial things, okay? But we won't go there, but this is all it means. I can average everything except the last eigenspace, okay? I know I can't average all the eigenvectors, but in my setup, I'm averaging eigenspaces completely or not at all. So I'm just saying leave out the last one and everything else is okay, okay? That's called an extremal design. So this was defined by Golubev in 2020. So let's look at some extremal designs. So here is the icosahedron again, and I want to order it this way, same ordering, and I want to average lambda 1, lambda 4, and lambda 3, leave out lambda 2, okay? So again, yeah, okay, now I see where the mistake was. So this is the slide, this is the correct slide, okay? So now I'm looking for 3 designs, right? I'm averaging 3 eigenspaces, lambda 1, lambda 4, lambda 3. So it's a 3 design, and that is an example of an arbitrarily weighted 3 design. That's extremal because it's leaving out only lambda 2. This is positively weighted, and if you look for a combinatorial one, you can't find one, but you can find one that averages the first 2. Okay? So this is the slide that we should have had before, right? Okay, so these are some examples of these designs. Okay. Oh, we got out of this somehow. Okay, so what is coming next? Is that all we have? Okay, so maybe that's all we have for today, but I mean for the slides. So this is what the designs are. Okay, is the concept clear? Okay, so now let me ask you. Okay, so first question is, do you see that finding those designs is the same thing as solving for this W? That is one question. Let me ask that first. Okay. So why? So finding designs means a collection of vertices with weights. Okay, and it should be able to average the first so many eigenvectors. In fact, eigenspaces, but let's say that we've caught all the eigenvectors in those eigenspaces, right? So that's the same thing, and let's assume we're only interested in positively weighted, okay? So this type of design we're never going to talk about, so don't worry about this. But let's only talk about positively weighted or uniformly weighted, okay? That's more interesting. That's the type of quadrature that people usually like to do. So then, do you see that that's the same thing as doing this? So let's maybe convince ourselves why, right? So the W's are like the weights. The W1, W2, W is an n-dimensional vector, but lots of its entries are 0, right? So it's really only supported on some small number of things. That's like the big W, the part of the vertices that we are picking, right? So let me write that. So, okay, I need a color. It's let's pick a color that you can see. All right, so think of the W. Let's erase everything we don't need here. Maybe, yeah. So W is a vector supported, so there's W1, W2, Wn, okay? So these are sitting on the different vertices of the graph. W1 is sitting on vertex 1, W2 sitting on vertex 2, and so on, right? But the support of my W is only L. This is N, okay? L may be quite small, right? So if so L is like the number of eigenvectors you're trying to average, that is L. So maybe so let's suppose L is 3, okay? So if L is 3, it's saying that, okay, something, maybe this one is okay, this one is there, and that one is there, and everything else is 0, okay? So W is a vector that only has support on 3 vertices. Everything else is 0. Okay? So W is non-negative. This part is not important. It will average the first, L eigenvectors. It'll also average this. We just calculated that, right? It averages that. So if I can find a W like this that has this property and this property, okay, this is not important, as I said, because you can always scale this. It's not important. This is really the crucial property. So if we can find a W that's non-negative and has this property, then that is really these colors that you see on the vertices, right? So it's saying that in the support of W, which are the colored vertices, you put some numbers, which are the values of the Wi, and everywhere else on the graph, you put 0. Which is the value of W in all those other vertices, okay? So finding a positively weighted design is exactly solving this system. Okay, we have half an hour to clear all the doubts.
Well, you could show the Mathematica, you were going to show something that looks like design.
No, it's hard to compute design, so let's actually talk about that too. But first I need you to understand this before we can talk about that. Okay, so if I could, okay, let me try again. So this we talked about in the morning, right? So I'm picking some collection of fees to average the first L in my ordering. Fee 1 comes for free, as I said, doesn't really matter. Let's even get rid of this because we just scaled it to have that property, so that's not so important. So if I can find a W non-negative that averages the first L eigenvectors, okay, that's the key, right? So did you agree that so doing this is the same thing as finding the global average? That's the part that I erased, right? So if a W can do this, it's also finding it's also letting you find the global average of the function on the graph, okay? So I claim that this type of W is exactly a design that averages phi 1 all the way up to phi L, okay? And let's assume that these two all together are the bases for some collection of eigenspaces, okay? So let's assume that the eigenspaces I want to average are spanned by these guys, okay? So I can pick the eigenspaces first, pick enough eigenvectors from those eigenspaces, that is my collection, okay? So if I can find a W like that, then it actually averages these eigenvectors and the eigenspaces that they are contained in. Is that okay? Yeah, Lavanya?
No, I wanted to just ask about if we have a fat eigenspace and I'm not considering all the possible eigenvectors of that space, how will that affect these arguments over
So this is saying that, okay, so any number of eigenvectors you can do that. Right?
Yeah.
So what is stopping us to define a part of subspace?
You can, okay, you can cut a subspace in the middle, but then some weird things will happen, okay? So if you cut a subspace in the middle and you find a design, then it turns out there's a different set of weights that can make you go all the way to almost the end of that eigenspace. So if the eigenspace had, say, 10 vectors and I only picked 5 to average, then there's a slight reconfiguration of the weights that can average up to 9 vectors. So you can almost get to the end. The thing is, how do you cut an eigenspace, right? Like how do you choose which basis vectors from an eigenspace to pick? There's nothing very special about it, right? There are infinitely many bases for an eigenspace. And then once you pick a basis, if you're only going to take a few of those vectors, which ones? It stops having any real meaning. That's why we are averaging the whole thing. But if you're seriously interested, I can show you the complications that will happen if you cut things. But nobody's stopping you from cutting it. You can, okay? So in this definition, I'm just picking some collection of eigenvectors to average. It could have spanned entire eigenspaces, or it could have cut some eigenspace somewhere in the middle. That's possible. I'm just saying that let's just go with the eigenspace definition because it's a little cleaner, okay? But if you're insisting on keeping the other definition, that's also fine. It works, okay? So just pick like a collection of eigenvectors to average. Okay, so the key thing is this, okay? So can we agree that finding this kind of W is the same thing as finding vertices in the graph with weights that can average those eigenvectors?
So you are assuming that whatever the matrix you're working has all one eigenvector.
Yeah, so the matrix is always either the walk matrix or the Laplacian or the adjacency. They all have the all ones.
Adjacency only.
Yeah. Assume regular. You can extend all this theory to non-regular, but it's more messy. So let's not try to do that, okay? I'm assuming d-regular from today till Friday, okay? There's nothing non-regular happening in between the two. So please assume d-regular, yes?
one more trivial question maybe. We are doing it like for the extremal design from the m-1 dimensional space, right?
m-1 eigenspaces.
Eigenspaces, m-1 eigenspaces or whatever it is.
Yeah.
So the one that we are leaving, it's not the all ones, right?
No, it's never the all ones.
All ones always.
You're always including the all ones. Because the all ones is for free. That's the exercise, okay? Any set can average the all ones. So all ones is for free. We're not even going to bother with it from tomorrow, okay?
So
but just stick it.
Can we drop it and look at the remaining spaces?
Exactly. So the hard part was this, right? This is the hard part where we had to work. This part came for free because phi1 is all ones, and no matter what you do, you're going to get, it's going to be okay. Okay?
But we didn't actually construct the W, right? We said there exists a W by Farkas.
Yeah, there exists a W by Farkas, okay? But can you see how to construct it? Let's talk about that. How do you compute it? So if you had to go home today and compute one of these, what system will we solve? Yeah, exactly. So we have to solve this. This is the U matrix. So I have to do, let's forget phi1, but we have to do phi2 up to phi L transpose W equal to 0. Okay, this is a linear system we have to solve. But you also need this, W non-negative. This is now in the world of linear programming. So it's saying that, so this is some subspace, right? The W's that satisfy this is a subspace. But I don't want the whole subspace. I only want the part that lives in the positive orthant. So I only want the part that lives in the positive orthant, okay? The positive orthant is bigger, but I intersect my subspace with the positive orthant. So I will get a cone, actually, okay? So I'm looking for something non-negative in this cone. I mean, sorry, it's here, but I don't want 0 either, okay? So I want, maybe what I will do is I will take the shaded cone. So this is my cone. In general, it's some cone, polyhedral cone, because I'm intersecting the positive orthant with the subspace. And then maybe I just want to slice this cone at height 1 or something. So I can assume that the norm of W is 1, okay? And then I want to find something in here. That's what I'm doing, okay? So we want to solve this, and let's also impose some condition on the norm or something like that. Okay, so this is what we need to solve, but we want to solve it with as few support vectors as possible, right? We want the support to be as small as possible. So in this picture, where should it lie if you want the support to, so the sides are coming from the positive orthant, right? I had a subspace, I'm cutting it with the positive orthant, so the sides of the cone that you're going to construct come from x1 grade equal to 0, x2 grade equal to 0, and so on, right? So that's where the sides are coming from. These are, each one of these sides is some xi equal to 0, and then you're on the other side of it. So where should we look if we want to find a very low support vector?
It should lie at the intersection of most of these.
Exactly, you want it to lie on the boundary, first of all, and on as many of your coordinate planes as possible. Do you agree? So the picture is not quite exactly like this, but in general, if you cut a subspace with a positive orthant, you will get some sides, and you want to be on as many sides as possible, right? That's like finding the sparsest vector in a cone, right? We're looking for the sparsest vector in a cone, right? But finding a sparsest vector even in a subspace is NP hard. Okay, so you can solve AX equal B, that's easy. But now if I ask you for the sparsest X such that AX equal B, but not 0, 0 is of course very sparse, right? But we don't like 0. So give me the sparsest vector in a subspace, meaning as many zeros as possible. That's hard, okay? And this is like the big work of Donahoe and company. This goes into like MRI machines and so on, right? So in MRI machines, what do you do, right? The MRI is taking, whatever, magnetic resonance, right? It's doing magnetic resonance imaging of your brain or whatever. You're inside the machine. And so what it's collecting is some signal vector. So it's collecting some signal vector B. This is the image, okay? And the measurements that you're taking is some given by the rows of some matrix, okay? So you have some AX equal B. And you want to do this with So you want to take very, very few measurements. You want to reduce the time inside an MRI machine. So think of putting a little child inside an MRI machine. I don't know if anybody of you have been inside an MRI machine. Have you? It's really scary, okay? It's this little coffin-like thing. They push you in there. Normally, they even let you close your eyes because it's really scary. It's like a tiny little thing. So imagine putting a little child inside an MRI machine, right? You want this measurement to be extremely fast. You don't want the kid in there for half an hour, which is what adults have to do. They have to lie in there for half an hour while they image your brain or whatever, right? Spine, whatever. But so the question is, if you have a very underdetermined system like this, so if I have only 50 measurements, but there are 10,000 columns in this thing, this is underdetermined, right? So this has infinitely many solutions. You agree? But we want something that's as sparse as possible. So that's like the key problem in like reducing the time inside things like MRI machines. And finding the sparsest vector in general is very, very hard. So there's all this wonderful work from like, I don't know, 10, 15, 20 years ago by statisticians and other people where they show you like approximation algorithms to find vectors that are pretty sparse, okay? Do you know a way to find a sparsest vector approximately? So we may not be able to find the best sparsest vector, but if I want to sparsify a vector, what might you try to minimize? L1 norm, okay? So what's your name? Abhishek. Abhishek knows this because he knows optimization, okay? So this is a standard trick. So if you want to minimize the sparsity, or maximize the sparsity, that's the zero norm of the matrix of a vector. This is not a convex function. So instead you minimize the one norm, okay? If you minimize the one norm, it's not quite same as saying you have lots of zeros, but you're at least making sure that the sum of the entries is small. So you can hope that there were lots of zeros and the only entries that survived were a few, okay? So the typical way to solve this is so what you could do approximately is to minimize the one norm of W subject to these equations, these inequalities, and maybe this condition. Okay, some normalizing condition so that you don't just get the zero vector back. Do you agree? So this you can do. This you can solve in a software. Okay, so we can find the sparsest. It's not the sparsest vector, but it's a proxy. It'll get you something close. Good. So this is how you would have to compute designs, right? You would have to find the sparsest vector that satisfies this equation, not zero.
Is it digression? Why does the two norm not work?
It's quadratic.
Oh, so you mean just in terms of computing? Yeah,
just in terms of computing. I mean, one absolute value you can rewrite as a linear program. But as soon as you have a quadratic objective, then it's harder. Okay. So in linear programming world, this is what people usually do. Okay. Okay. So that's a very unsatisfactory place to end because it's saying that, okay, these designs are great. They exist. By Farkas, they exist. There's always something of dimension less than L, right? But how do we actually find them? Like if you want to actually find them, you have to solve the system. So on the computer, this is how you would do it, right? You just plug all this in, ask the computer to minimize. Mathematical will also do this. It'll give you something back, okay? But maybe you can't really get something that has support at most L, which is what Farkas will guarantee you, right? There's something of support at most L. Theory will guarantee you that. Okay, so then tomorrow, we're going to see exactly how to organize these designs and a structural theorem that will show you how they live. Like what is the space of all designs and how can you actually compute them for some examples. It's going to be hard no matter which way you look because the computation is not easy, okay? So it's all like NP and whatnot, but it's fine. So there's always this piece is telling you there's always a design of size at most L if you're trying to average L things, okay? So ideally we want to find those guys, the guys that have size at most L, not bigger sizes, right? There are always things of bigger size, but you want to find size at most L. Okay, so that maybe this is a good place to end at least my part.
You had some mathematical thing that you did not run?
Yeah, maybe. Let me take a look at it. Okay, so I said a lot of things.
I think it's open.
Oh, it's open. I think I closed it. So let's see. Okay, so let me just evaluate this and let's see what happens. Oh yeah, so this is one of the exercises, I think. Okay, let's maybe just look at the exercises before we end. You all have the exercises, right? Where did I put it? Yeah, okay. Okay, so number 1 exercise says, compute the Laplacian designs of the cube that average entire eigenspaces in increasing order of eigenvalues. Okay, this is what this is doing. So this is the cube graph in the very top. I computed the Laplacian of the cube graph. Okay, we already had the cube graph up here somewhere. This was the cube graph, right? That's the cube graph. And then here I'm computing the Laplacian of the cube graph in the first line. Everybody see that? The L is the Kirchhoff matrix of the cube graph. Then I'm writing down its eigenvalues. This is PSD. So it's going to start in 0, then it has an eigenspace of multiplicity of dimension 3, another one of dimension 3, and one of dimension 1, right? And then I ask for the eigenvectors. So here are the eigenvectors. And then I put them in the rows of a matrix. Okay? So this one goes with eigenvalue 0. These 3 go with eigenvalue 2. The next 3 go with eigenvalue 4. And the last one goes with eigenvalue 6. Okay? So I'm asking you to just find designs that can average, let's say, these 3. That's the first 3. Or the first 3, or the next 3, or both, okay, or just this one. So you can pick which eigenspace you want to average. Can you find vertices on the cube that'll do the job? Can you do just the last eigenspace? There's only one eigenvector in the last eigenspace, okay? Can you find corners of the cube, or the vertices of the cube graph that'll average just that last eigenspace? What's the smallest design you can find? Okay, that's the cube. I just want to average the last one. So which vertices can you pick so that with weights, let's say? So if you just pick this first vertex, it's not okay, right? There's no way I can weight this to get 0. What if you pick these two? That'll work, okay? Or you could pick this and this, for example, okay? So in this example, you just need 2 vertices to average the last eigenspace, okay? So if I pick the first and the last, then that's saying that the design is made up of this vertex and this vertex, with weight 1 here and weight 1 here, right? So I'm doing 1 times minus 1 plus 1 times 1 is 0.
It's a combinatorial.
It's a combinatorial design. And on Friday, we'll see these are orthogonal arrays. Yeah, they're very nice. Okay? Yeah, so the last one is easy. Everybody agree with that? The minimum size of a design is 2 for the last eigenspace. You can, of course, take this one and this one and this one and this one. That will also do the job, right? With uniform weights. But now that has size 4. It's less interesting. We want the smallest cardinality designs, okay? So 2 will do the job for the last eigenspace. How about this one? Do you see anything for the first 3? Fourth and the fifth. So this and this together? Yeah, that's a good one. You see that? If I pick the fourth and the fifth vertex, that'll also average to 0. Great, very good. Okay. So then the size is again 2 in this example. Sorry? This one? Oh, last one, yeah. Fourth and fifth also averages that. How about this one? These 3? The mid. The first 4 will do the job, right? The first 4, if you add them up, you'll get 0.
2 to 5. 2, 3, 4, 5.
2, 3, 4, 5. The first 4 is correct. First 4 will work. And the last 4 will work. Right? So 4 seems to be the minimum size. Can you do 2? Or 3? You definitely cannot do 1. Do you agree? There's no single column that is 0 in the whole thing. Okay, so 2 is good. We didn't get 2. We got 4, right? We got 4. Can you do 2? That means some column has to be the negative of the other column, if you want combinatorial designs. Yeah. But you're allowed to put weights, okay? So 2 is going to be the best if it exists, right? Because we know we can't do 1. So is there a weighted way can we weight the columns so that they sum to 0?
So second, third, and fourth.
Second, third, and fourth. Second, so we're looking at these 3. Second, third, and fourth?
No. We are looking at this eigenspace.
Yeah, we're looking at this eigenspace, the eigenspace with these 3 rows.
For the second, third, fourth, we already got 2.
Yeah. So this is the problem of finding designs, okay? So Bifurca should exist. There's always something of size at most L, which is the number of things we're trying to average. Okay, this is known in many communities. It's also known as the Chokolov theorem, Chokolov bound. So many people know this result in many ways, and tomorrow we'll see yet another way to prove this result. So it exists, and that's how you compute it on the computer. Okay, you get approximately the correct thing. But to actually find it is NP hard.
So you're saying there's a 2 design,
No, there is probably not in this example. There probably isn't. Yeah.
3 maybe.
Yeah, I think for the cube you can prove that.
I can show.
You see 3?
Because the fourth and fifth columns are -1,
Yeah.
are constant.
Fourth and fifth.
So actually I can get a 2 design if I am allowed arbitrary weights.
Okay, what would you do?
I would take weight 1 for the fourth and -1 for the fifth.
Weight 1 for the fourth and?
-1 for the fifth.
Okay. So if you allow no weight restriction, yes, this is a design. That's true.
So what is the result that is taken? There is this subset.
There's no proper subset that can average all the eigenvectors.
So like 4 and 5 here, that will not average all the elements.
Non-negative, is it?
Non-negative.
No, but the weights I took are
No proper subset. I mean, for that here you can see 4 and 5. It kind of optimizes almost everything, but not all.
Yeah. So try to write it down. Assume there is something that can average everything, and you'll see immediately there's a contradiction. Okay?
One subset cannot do for all these things.
Yeah. One subset cannot average everything, and it comes from the orthogonality with the all ones. Okay, that's actually the key piece.